Hello, Dr. Tullis here. We are starting Chapter 9, Chemical Quantities and Reactions. And I just had to show off my chemical shirt that says, "Stop, I'm arresting you for assault." And then it says, "You'll never catch us alive, copper." Let's get started on Chapter 9. This chapter's career focuses on an environmental scientist. They monitor environmental pollution, including pollution levels in the soil, air, and water, as well as noise and radiation levels. They specialize in air quality and hazardous and solid waste. They monitor indoor air for allergens, mold, and toxins, and measure outdoor air pollutants. And they help in cleanup and remediation efforts. Section 1 is looking at the conservation of mass. You'll be able to calculate the total mass of reactants and the total mass of products in a balanced chemical equation. The law of conservation of mass indicates that in an ordinary chemical reaction, matter cannot be created or destroyed. There is no change in total mass that occurs in a reaction, and the mass of the products is going to be equal to the mass of the reactants. Tarnish forms when silver reacts with sulfur to form silver sulfide. This is our tarnish. The law of conservation of mass states, in this example, my reactants have a total mass of 247.9 grams, and notice that my products have 247.9 grams. In this balanced chemical reaction, notice that I have 2 in front of Ag, because on the right I have 2 Ags. I have 1 sulfur, and on the right I have 1 sulfur. So I have a balanced equation. This 2 means that I have 2 moles of silver. So that means I'm going to take 2 times silver's mass on the periodic table plus 1 mole of sulfur, and sulfur has a molar mass of 32.07 grams. And then if I add up on the right side 2 Ags and 1 S, that would give me that same molar mass. Here's some information that we can get from a balanced equation. Not only do we have that equation, we can see our reactants and our products. We can see how many atoms or formula units there are from that balanced reaction. We can look at Avogadro's number of atoms. We can see how many moles there are of each of the reactants and products. We can see the mass of each of the reactants and the mass of the product and how the total mass aligns. Let's look at a sample problem. The combustion of methane with oxygen produces CO2, H2O, and energy. Let's find the total mass of the reactants and the products for when 1 mole of CH4 reacts. We write our equation here. We have our reactants on the left, and if I have CH4, I'm going to look at my periodic table and take 12 plus 4 times hydrogen's mass and get about 1604. Then I'm going to add up 4 oxygens, which should give me about 64 grams. Add those 2 up, and I would have 80.04 grams of reactant. Now let's add up 1 carbon and 2 oxygens. That would give me 44.01, and 4 H's and 2 O's, which should give me a mass of 36.03. That would give me 80.04 grams of products. Hopefully by now you feel comfortable finding the mass of the reactants and the mass of the products. Moving on to section 2, we are looking at mole relationships in chemical equations. You will be able to use a mole-to-mole factor from a balanced chemical equation to calculate the number of moles of another substance in the reaction. A mole-to-mole factor is a ratio of the moles of 2 substances in an equation. In this case, we have iron plus sulfur to give me iron 3 sulfide. We can see that we have a balanced equation because in order to make iron 3 sulfide, we need 2 Fe's with a plus 3 charge to have an overall plus 6 on the left, and 3 sulfurs. Each sulfur has a negative 2 charge. That would give us a neutral equation. So in order to balance this equation, if I have 2 irons on the right, I need 2 irons on the left. 3 sulfurs on the right, I would need 3 sulfurs on the left. And from that balanced equation, I can write ratios of the 2 substances. For example, if I wanted to look at iron versus sulfur, I would say that I have 2 moles of iron to 3 moles of sulfur. Or I can flip-flop this, and I could say that there's 3 moles of sulfur for every 2 moles of iron. I can also compare iron and the iron 3 sulfide. There's 2 moles of Fe needed for every 1 mole of product. Or I can say that for every 1 mole of product, 2 moles of Fe was needed. I can do the same thing with sulfur and product. 3 moles of sulfur needed to create 1 mole of product. or 1 mole of product for every 3 moles of sulfur. Why do we need to know those ratios? Well, because if I know that I have 1.42 moles of iron and I want to know how many moles of sulfur are needed to react. So I want to hop from one substance to another. And in order to do that, what do I want? I want moles of sulfur. And what have I got? I've got moles of iron. Again, what have I got is what I'm starting with. Now I need to look at that ratio. Moles of sulfur on top. I have 3 moles of sulfur for every 2 moles of iron. And if I do 1.42 times 3 divided by 2, I should get with 3 significant figures because I started with 3 significant figures. Don't let that exact quantity mess up your significant figures. I should get 2.13 moles of sulfur is needed to react with 1.42 moles of iron. Here's a sample problem where we have propane gas, C3H8. We know that it will undergo a combustion reaction, so we have plus oxygen to give us CO2 and H2O. We want to know how many moles of carbon dioxide can be produced. So we want to get to here. And we are starting with 2.25 moles of propane. I started writing this, it's a little sloppy, but here's my starting point. It's what my problem is giving me, 2.25 moles of propane. What do I want? My problem wants moles of CO2. And what have I got? I've got moles of propane. So here is my ratio. I need how many moles of CO2? There's 3 moles of CO2 for every 1 mole of propane. All that's left to do is plug and chug. 2.25 times 3 divided by 1. With 3 significant figures in my final answer, I should end up with 6.75 moles of CO2. Take a minute to look over the learning goals to make sure that everything makes sense.